Hi everyone! Welcome back to our X-Chem YouTube channel. I'm Taylor, and today we'll be talking about a very important part of all the reactions on Earth, catalysts. So before we begin, I'd like to give a quick thank you to our sponsors Actua and PromoScience for funding these awesome opportunities. Now, let's get into it. Before talking about what catalysts do, we need to know what they are. The scientific definition of a catalyst is a substance that increases the rate of reaction without actually being consumed in the reaction. So we've talked about reaction rates before and how we can change them using temperature, surface area, and agitation, and catalysts are just one way to change them as well. So in case you don't remember, the rate of reaction simply means how quickly a reaction between two or more chemicals takes place. Certain reactions need a catalyst, or else they won't happen on their own. For instance, hydrogen peroxide, or H2O2, gradually decomposes over time into oxygen and water. The reaction is so slow that we don't even notice it happening. However, if we use a potassium permanganate catalyst, the reaction occurs much faster, and we can see it happen before our eyes. So think of a catalyst like an officiant at a wedding. You have the two people getting married, which represent two substances in the reaction. They can't get married on their own. They need an officiant to do it for them. The officiant decides how long the ceremony lasts. He can either be really slow with it or very fast. And in the end, with the two people getting married are changed by the ceremony, the officiant is no different. He did not get married. He simply helped the two people do so. So, to demonstrate a catalyst in action, we have a little experiment set up with cobalt chloride. So I'm going to bring my friend Caitlin in. So, here it is. As you can see, cobalt chloride is naturally a reddish pinkish color. In this experiment, we're going to use it as a catalyst for the reaction between hydrogen peroxide and sodium potassium tartrate. So we have the sodium potassium tartrate in the beaker, and we're going to, it's already been heated, we're going to add it into the glass cylinder. And soon enough, we're going to add some hydrogen peroxide as well. But before we do that, what we're looking for when we add the hydrogen peroxide is signs of a reaction. Does anyone know what these signs are? Shout it out in the comments. There's tons of right answers for this one. So some reactions occur without any visible indication though. While I'm waiting for these comments, I'll just talk about that. Sodium hydroxide and hydrochloric acid will react together to neutralize in solution, and we ourselves can't see this happening. So in these cases, we use visual aids to see what's happening, such as indicators. So we use phenolphthalein to show us the reaction that's taking place there. It changes color from clear and colorless to light pink to tell us when this reaction has taken place. So we'll be doing an experiment later on in this video that requires one such visual aid, known as a glucose testing strip, but we'll talk about that later. Does anyone have any ideas on signs of reaction? Basically just some indicators with our senses that we can tell that something's happening there. Okay, well, some of the signs would be like color change or some bubbles forming. It shows the formation of a gas. We could also look for temperature change, some odors coming off of it, some formation of precipitate. Those are the main things that we look for to show that there is an obvious reaction happening. So let's see what happens when we add the hydrogen peroxide in. Oh, I just got some comments. Yep, you guys are exactly right. There must have been a delay there or something, but we'll add the hydrogen peroxide in now. And as you can see, there's some bubbles forming, but not much else is happening. So these two substances, they want to react, but they need a catalyst to help them do so. So we're going to add our cobalt chloride now, and I'll let you see what happens. So keep an eye out for signs of reaction. It's going to take a minute for this reaction to take off, so let's just talk a bit about catalysts in the real world. Catalysts have many, many, many uses in all realms of life, from starting your car to making bread. So catalysts have existed naturally since forever in places like our body and in nature, but we also have started using them for much more in our technology. Catalysts have become super useful in combating global warming. So catalytic converters in cars, such as palladium and platinum, they're used to turn pollutants from car exhaust into less harmful substances in the environment. But not all catalysts are good for us either. Chlorofluorocarbons, also known as CFCs, were widely used in refrigerants and aerosol sprays a little while ago, but these tiny particles float up to the top of the atmosphere, and then they break down after a while, and we get loose chlorine atoms in the air, or our stratosphere, which in turn act as a catalyst and break down our ozone layer into monoatomic oxygen. So the ozone layer is super important. But so in 1996, international agents signed an agreement to not use CFCs anymore. But the experiment's taken up, so So as you can hopefully see, there's a big color change happening here. It turned almost like a root beer color, kind of like a dark brown, almost a little green too. And a lot of bubbles are forming right now. Those are some clear signs that a big reaction is happening right now. So let's keep an eye on it. Something else is going to happen soon. So as you can see, it's dying down pretty quick. And it's turning back to pink, the original color. So let's talk about why this happens. When we added the cobalt chloride, it kickstarted the reaction between the hydrogen peroxide and the sodium potassium tartrate. The solution turns a dark green color and as a result starts to bubble up a ton. And then when the reaction's done, it simply just stops bubbling really quickly actually and turns back to the pink color of the cobalt chloride. Because the catalyst is not consumed, the color of it gets restored at the end. So that's just a cool little demo on how catalysts work and how they get regenerated. Thank you, Caitlin. We're going to move on to something new, or not so new. So remember the reaction we were talking about before? This is the decomposition of hydrogen peroxide into oxygen and water. I'm sure most of you have heard of something called elephant's toothpaste, but did you know that it was also a catalytic reaction? So I'm going to bring Caitlin back in. And we're actually going to do that here. So what we have here is hydrogen peroxide in a beaker. We have some dish soap, a little bit of water, warm water, and some yeast, and also some food coloring, just for kicks. On its own, the hydrogen peroxide is slowly decomposing, but it's so slow that we don't notice. If we add some yeast to it, something really cool will actually happen. So what we're doing here, we're just going to activate the yeast with the warm water. It takes a couple seconds, so we just swirl it around a little bit, and then that should be enough. Now we add a little bit of dish soap. I'll explain why in a bit. Some food coloring so you can see it better. And then finally, after we stir it up a little, we'll add the hydrogen peroxide. So that's our elephant toothpaste. Pretty cool. Thank you, Caitlin. Let's talk about why this happens. Yeast is a living thing, and all living things contain a catalyst known as catalase. The catalase can react with the hydrogen peroxide to make it decompose much faster into water and oxygen gas. So when the oxygen gas is formed, it gets stuck in the soap that we mixed in, and we get this giant foamy mixture as a result. So catalase is a special kind of catalyst. It's known as an enzyme. So enzymes are catalysts that are produced by living things, and they act on specific biological reactions. Enzymes are found all over your body in nature, and they help you survive. It's important to remember that all enzymes are catalysts, but not all catalysts are enzymes. Think of enzymes as very specific biological catalysts. While a catalyst can act on multiple reactions to speed them up, enzymes are designed to speed up one specific reaction. Each different enzyme fulfills a specific purpose. So naturally, since there's only one type of enzyme that can act on one specific reaction type, there are many, many different enzymes in the world. Because of this, the substances that enzymes react are called substrates. Because the enzyme is perfectly structured to target the specific substrate, the substrate will fit perfectly into the enzyme at a place called the active site. Here, the substrate will undergo a reaction with the help of the enzyme, and once reacted, it will be on its way. The enzyme is not used up by this, since it's a catalyst. So we call this the lock and key model, where the enzyme is the lock and the substrate is the key. Like a key, only the correctly sized and shaped substrate can fit into the correct active site, similar to a keyhole, or on the enzyme, or the lock. So another interesting enzyme that we are going to talk about today is pectinase. It breaks down pectin, which is a protein found in plant cell walls, especially those cell walls in fruits. In fruit juices and jams, pectin is used to keep the mixture together and increase thickness. So I'm going to bring Caitlin back in. So here we have 2 beakers of jam, and which contains pectin. And we'll add water to one and pectinase to the other. And since pectinase breaks down pectin, which makes jam thick, What do you think will happen to the jam with the pectinase mixed in? So we've added it in. We're going to mix it around a little bit. It's going to take a few minutes to react. So we're going to set it aside for now, and we're going to move on to something new in the meantime. So we'll come back to this shortly. Another example of an enzyme in our body is lactase. So lactase is found in our stomachs, and it's a very important step in our digestive process. Lactase breaks down lactose and dairy products into simple sugars like glucose that our body can use for energy. We have a quick demonstration to show for this. So here we have two test tubes, and they're both half full with lactose solution. So that's all that's in there. We're going to add some lactase to one of them, and after a bit, we're going to see what happens. So we're just going to add a couple squirts, and that should be enough. So remember, one of these test tubes has lactose and lactase, and the other one just has lactose. So while we're waiting for this to process, let's talk a bit about lactase. While it's naturally found in our bodies, it can also be collected and sold medicinally too. So the lactase we use in this experiment comes directly from lactate pills. Sometimes certain people aren't able to break down lactose into sugars on their own. Because the lactose does not get broken down, it can cause some nasty things like stomach aches. We call this lactose intolerance, and it's actually pretty common. That's why pills like these exist, so they help the body with the digestive process. So now when we go to test these solutions, we're going to use something called a glucose testing strip. How it works is that it'll change color depending on how much glucose it detects. So remember, lactase breaks down lactose into glucose. So the more lactase there is, the more glucose there should be. So I'm going to pull up this little scale here. This is the scale for the glucose testing strips. A negative result, meaning no glucose detected in the solution, is this bluish turquoise color. The more glucose there is, the more green and then brown it will turn. So let's see what these let's see what color these strips turn when we test the solution. So those are the strips. They both have the negative result right now. And we're going to add one to both solutions. And it takes just a second for them to develop. So now I'm going to make So as you can see, there's a slight difference there. It's still developing. The one on the right is a little more green than the one on the left. So that shows that there was glucose detected in the solution, and more so than there was in the lactose, because the lactose actually has no glucose at all. It's a negative test. If we dip it in one more time, it might be a little more obvious, because it still is reacting in there. It's still breaking it down. So there we go. That's a little more green. It's almost an olive color there. So that shows that there is actually quite a bit of glucose there already, and it will only get darker with time. So that is lactase. Now, our pectinase should be just about ready. So we can go back to that. So what we're going to do, we're going to transfer the jar's contents into these funnels there, and we're going to watch the juices fill out the graduated cylinder. So before we do so, which jar do you think will contain more juice? The one with the enzyme or without? Remember that pectinase breaks down pectin in jam, making it thinner and less viscous. Okay, so as it's dripping down, we can already see that there's a lot more liquid in the pectinase jar than the water one. That's because the jam was processed by the pectinase. So the cell walls of the fruit contain pectin, which holds them together and keeps the jam thick. The pectinase dissolves these cell walls and turns the jam into juice. So that just about concludes our presentation on catalysts and enzymes today. Does anybody have any questions? And there is a bit of delay, so I'm just gonna wait a couple more seconds in case anyone has questions and I just don't see them. Okay, well, I'm not seeing any questions. So if there's no questions, I'm just gonna end the video now. Don't forget that we have new live streams every Tuesday, Wednesday, and Thursday at 10 a.m. now, not 2 p.m. anymore, it's 10 a.m. Thank you all for coming today. We'll see you later.